we have a non-ideal inverting operational amplifier. And we're going to analyze it and then compare our analysis to that of an ideal inverting amplifier. That's coming up right now.
Hi, I'm Dr. Bob. There are no lectures here. I just solve problems, homework problems to help you understand how to do them. Electrical engineering, lecture service.
Alright, part 1b is to calculate Vn when Vg is equal to 60 millivolts. Alright, so we have an input voltage of 60 millivolts, and let's go back and look real quick what Vn is. Vn, and we're going to use the large model here. Vn is this right here, and of course that's going to be compared with the VP, and our output is going to be the gain times VP minus Vn. So it's going to be a 0 minus whatever this voltage is, and that's going to give us our output. So we have some formulas we can start with, and the first formula, of course, is the gain formula that we just worked out, V out over Vg is equal to minus 19.87. So with that, we just take our Vg is equal to, well, 60 millivolts, and then we have V out is equal to minus 19.87 times 60 millivolts, and of course that's just this formula right here, and for that we get V out equals to minus 1.192 volts. Alright, so that's the first little piece we can get. Another thing that we're going to do is going to modify one of our equations, and I'm going to call it equation 3. Let's go get the equation that we have for this. Is going to be equation 1, but a modified version of it. So equation 1 here is Vn times 65 plus Vg times minus 60. So we're going to use that one because we already have a V out and a Vg, so those are going to drop out and we're just going to get Vn. So that's pretty easy to do. We just equation 3, which is a modification of equation 1, is Vn times 65 minus 60 times Vg minus 3 V out equals to 0. And of course we have Vg is already given as 60 millivolts, and V out is minus 1.19, and we just solve for this. Vn is equal to 60 Vg plus 3 V out divided by 65, and then of course you just drop those numbers in. Well, let's drop them in. 60 times 60 millivolts plus 3 times minus 1.192 volts, and that's divided by 65. And of course you can do those numbers. We get a V sub n equals to 369 microvolts. And that's the answer to part 1b. Okay, so in part 1c is to calculate the resistance seen by Vg. And for this part of the problem, we've basically drawn a model of all the resistance and all the power sources in order to resolve it. So what we're looking at is where Vg is this right here, and it's kind of looking into the circuit. As you can see, I've got a couple of arrows drawn here, and these two arrows are saying, well, what resistance is it seeing, and how do we figure out how those resistances are worked out. So the simple solution, of course, is that R of VG, no, it's good, R of VG is just going to be equal to VG divided by IG. Okay, well, so IG is going to be the current coming out of here. So, how do we find that? Well, of course, that's going to be pretty simple. That so we know VG. It doesn't matter what VG is. We have it as 50 millivolts. But when we get IG in terms of VG, then we can get the VGs to cancel out. So IG is just equal to VG minus VN divided by the 15K ohm resistor. So that's one simple solution, but maybe not so simple. We're going to have to get a relationship between VG and VM in order to do that. But we do have some relationships we can use. The first one we're going to start out with is Vn is equal to minus 121 V out divided by 400K minus 1. We have that relationship. We also have that V out is equal to, that's our gain relationship, minus 19.87 times VG. And then, of course, we can substitute. That comes from V out over VG equals to minus 19.87. So we have that. So we can drop that VG right into there. We have then V sub n equals to minus 121 times minus 19.87 VG divided by 400,000 minus 1. And from that we get just V sub n is equal to 0.006 VG. So now we have that relationship. And then let's go ahead and pull, I'm going to write it over here actually. From that we can go to, now over here is good. I sub G equals to VG minus 0.006 VG divided by 15K ohms. And that comes out to IG equals to 0.000662667 VG. So that gives us that R VG is equal to VG divided by this long number IG, which is 0.000662667 VG, and we get an RVG equals to about 15.09K ohms. Okay, so that takes care of this part right here. Okay, for part 2, it's basically work out repeat steps A, B, and C for this case if the operational amplifier is ideal, and then compare the results. So let's take a look at what happens here. We calculate the voltage gain, V out over VG. In order to do that, we just have to use, again, we're going to use a simple KCL, Kirchhoff current law. Look at the voltages or the currents going in these two directions. It's going to be Vn minus Vg over 15k ohms plus V in minus V out over, it's an out, over 300k ohms plus I in. Now in this case, all that adds up to 0. In this case, the I in is just going to be equal to 0, so it's not going to do anything. And we can get, let's see, V out over V, and we can get a solution pretty quickly. V in, since this is ideal, V in equals VP and VP equals 0, or we can just say V in equals to VP, which is equal to 0. So this also goes away, simplifying our problem very equally. We get minus VG over 15k ohms plus minus V out over 300k ohms, and that's equal to 0. And then, of course, I'm going to let you do the algebra on this. Is going to be V out over VG is equal to minus 20. So that's all of our voltage gain, and that compares with a what we got before, the non-ideal case, V out over VG, non-ideal, and I was equal to minus 19.87, which was pretty close to our minus 20 right here. The part 2b is calculate Vn when Vg is equal to 60 millivolts. Of course, we know that V sub n is equal to V sub p, which is equal to 0 in the ideal case. In the non-ideal case, we had V sub non-ideal. We had V sub n was equal to 369 microvolts, which is 1/3 of a millivolt, pretty close. So it's pretty low, and idealized, of course, to 0. So part C is, in the ideal case, calculate the resistance seen by Vg. Once again, we use that same formula. Vg is just here at the input, and we can probably pretend there's a Vg right here, right, and it is attached, and we're looking at the resistance going into the circuit. So R of Vg is just going to be Vg divided by IVG. I'm going to call it IVG, and that's going to be, we know that Ig, which is this current right here, is just going to be equal to Vg minus Vn divided by 15k ohms. Well, in the ideal case, of course, Vn equals to 0. And what do we get when we plug in? Ig is R of Vg is just equal to Vg divided by Vg over 15k ohms. These two cancel out, and of course you get R of Vg just equals to 15k ohms. And that is the answer to part C. When compared to the non-ideal case, we got R Vg was equal to 15.09k ohms. So it was very close, and that completes this problem.
Thanks for watching my program.
If you like my videos, be sure and subscribe to my YouTube channel. And for an organized listing of my YouTube videos, go to my website, www.wherearemyplacebos.com, and click on videos. Have a great day.